The National Electrical Code, specifically Section 210.8A7, mandates ground fault circuit interrupter, or GFCI, protection for all receptacles installed in dwelling units within 6 feet of the outside edge of a sink. This requirement applies to all sinks within a dwelling unit, irrespective of their specific location or function. Now let's shift our focus to non-dwelling units. Section 210.8b outlines the GFCI protection requirements for receptacles in locations other than dwelling units, most notably including bathrooms. It's important to understand that 210.8b is not an exhaustive list. It doesn't override or supersede the broader and more general requirements outlined in 210.8a. Addressing sinks in non-dwelling units, while Section 210.8b doesn't explicitly mention sinks outside of dwelling units or bathrooms, the core intent of GFCI protection is to safeguard against electrical shock hazards, particularly in environments prone to moisture or dampness. Given that sinks inherently introduce the potential for wet or damp conditions, it's a logical and justifiable interpretation to extend GFCI protection to receptacles situated within 6 feet of a sink's outer edge in non-dwelling unit settings as well. This interpretation aligns with the overarching principle of the NEC, which is to ensure robust protection against electrical shock hazards. In situations such as elementary schools, where sinks are commonly found in classrooms, and optical shops with sinks in various work areas, requiring GFCI protection for nearby receptacles is a prudent safety measure. Even if the NEC doesn't explicitly spell out this requirement for every conceivable non-dwelling location, the underlying principle of protecting against electrical hazards in proximity to water sources strongly supports this approach. If an electrical contractor were to challenge the necessity of GFCI protection in these scenarios, a defense of this position could be built upon the rationale that I've just explained. The core argument rests on the recognized potential for wet or damp conditions around sinks and the general mandate within the NEC to mitigate electrical shock risks. It is important for electrical inspectors and contractors alike to understand not only the letter of the code, but also the spirit behind it. The NEC is designed to be a living document, constantly evolving to address new technologies and safety concerns. While it may not always be possible to provide explicit guidance for every conceivable situation, the underlying principles of electrical safety should always guide decision-making. To further clarify the requirements for GFCI protection, let's consider specific scenarios and how the NEC might be interpreted in each case. Firstly, in a dwelling unit, any receptacle within 6 feet of a sink, regardless of the sink's location, requires GFCI protection. This includes kitchen sinks, bathroom sinks, laundry room sinks, and even utility sinks in a garage or basement. The purpose of this requirement is to protect occupants from electrical shock hazards while using electrical appliances near water sources. Secondly, in a commercial kitchen, GFCI protection is generally required for all receptacles serving countertop areas, as specified in Section 210.8b2. This is because commercial kitchens are often wet and damp environments, and the risk of electrical shock is higher. Thirdly, in a healthcare facility, GFCI protection is required in patient care areas, as specified in Section 517.20. This includes receptacles near sinks in patient rooms, examination rooms, and treatment areas. The purpose of this requirement is to protect patients from electrical shock hazards, as they may be more vulnerable due to their medical condition. Fourthly, in an industrial setting, the need for GFCI protection near sinks may depend on the specific conditions of the environment. If the area around the sink is typically dry and there is no significant risk of water splashing onto electrical equipment, GFCI protection may not be required. However, if the area is wet or damp, or if there is a risk of water splashing onto electrical equipment, GFCI protection is recommended. Fifthly, in outdoor locations, GFCI protection is generally required for all 120 volt, 15 amp and 20 amp receptacles, as specified in Section 210.8A3. This includes receptacles near outdoor sinks, such as those in a patio or deck area. The purpose of this requirement is to protect people from electrical shock hazards while using electrical appliances outdoors. Now let's consider some common misconceptions about GFCI protection. One misconception is that GFCI protection is only required for receptacles near water sources. While it is true that GFCI protection is often required near water sources, it is also required in other locations such as construction sites, garages, and unfinished basements. Another misconception is that GFCI protection is only required for 120-volt receptacles. In fact, GFCI protection is also required for some 240-volt receptacles, such as those serving electric dryers and electric rangers. Another misconception is that GFCI protection is not necessary if the electrical system is properly grounded. While grounding is an important safety measure, it does not provide the same level of protection as GFCI protection. A ground fault can still occur even if the electrical system is properly grounded, and a GFCI will trip and interrupt the flow of electricity in the event of a ground fault. To ensure that GFCI protection is working properly, it is important to test GFCIs regularly. This can be done by pressing the test button on the GFCI device. If the GFCI does not trip when the test button is pressed, it should be replaced. It is also important to inspect GFCIs regularly for any signs of damage or wear. If a GFCI is damaged, it should be replaced immediately. When installing GFCI protection, it is important to follow the manufacturer's instructions carefully. This will ensure that the GFCI is installed correctly and will provide the intended level of protection. It is also important to use the correct type of GFCI for the application. There are different types of GFCIs designed for different purposes, such as standard GFCIs, weather-resistant GFCIs, and tamper-resistant GFCIs. The NEC provides specific guidance on the selection and installation of GFCIs in various locations. This guidance should be followed to ensure that GFCI protection is effective and reliable. In addition to GFCI protection, there are other safety measures that can be taken to reduce the risk of electrical shock hazards. These measures include using properly insulated electrical cords, avoiding the use of extension cords whenever possible, and keeping electrical equipment away from water sources. It is also important to educate children about electrical safety and to teach them how to avoid electrical shock hazards. By following these safety measures, it is possible to significantly reduce the risk of electrical shock hazards and to protect people from injury or death. The NEC is a complex and comprehensive document, and it is important to stay up to date on the latest changes and revisions. This can be done by attending continuing education courses, reading industry publications, and consulting with electrical experts. By staying informed about the NEC, electrical inspectors and contractors can ensure that they are providing the highest level of electrical safety. In summary, GFCI protection is an essential safety measure that can help to prevent electrical shock hazards. The NEC provides specific guidance on the requirements for GFCI protection in various locations. By following the NEC and taking other safety precautions, it is possible to significantly reduce the risk of electrical shock hazards and to protect people from injury or death. Let's explore some additional scenarios and considerations related to GFCI protection and the NEC. Firstly, consider a situation where a receptacle is located more than 6 feet away from a sink, but a person could easily use an appliance plugged into that receptacle while standing at the sink. In this case, it is generally recommended to provide GFCI protection, even though it is not strictly required by the NEC. The rationale is that the person is still at risk of electrical shock while using the appliance near water. Secondly, consider a situation where a receptacle is located behind a sink, making it difficult to access. In this case, it may be tempting to forego GFCI protection, arguing that the receptacle is not likely to be used. However, it is still recommended to provide GFCI protection, as someone may eventually need to access the receptacle and use it near the sink. Thirdly, consider a situation where a receptacle is located in a finished basement. The NEC requires GFCI protection for all receptacles in unfinished basements, but it does not explicitly require GFCI protection for receptacles in finished basements. However, it is still recommended to provide GFCI protection in finished basements, as they are often damp and prone to flooding. Fourthly, consider a situation where a receptacle is located in a garage. The NEC requires GFCI protection for all 120 volt, 15 amp and 20 amp receptacles in garages, but it does not explicitly require GFCI protection for 240 volt receptacles in garages. However, it is still recommended to provide GFCI protection for 240 volt receptacles in garages, as they may be used to power appliances that are used outdoors, such as electric car chargers. Fifthly, consider a situation where a receptacle is located in a laundry room. The NEC requires GFCI protection for all receptacles within 6 feet of a laundry sink, but it does not explicitly require GFCI protection for receptacles that are not near a laundry sink. However, it is still recommended to provide GFCI protection for all receptacles in laundry rooms, as they are often damp and prone to flooding. Now, let's discuss the different types of GFCIs that are available. Firstly, there are standard GFCIs, which are designed for general purpose use. These GFCIs are typically installed in receptacles or circuit breakers. Secondly, there are weather-resistant GFCIs, which are designed for use in damp or wet locations. These GFCIs are typically installed in outdoor receptacles or in bathrooms. Thirdly, there are tamper-resistant GFCIs, which are designed to prevent children from inserting objects into the receptacle slots. These GFCIs are required in dwelling units and childcare facilities. When selecting a GFCI, it is important to choose the right type for the application. Standard GFCIs are suitable for most indoor locations, while weather-resistant GFCIs are necessary for outdoor locations and bathrooms. Tamper-resistant GFCIs are required in dwelling units and childcare facilities to protect children. It is also important to consider the ampacity of the GFCI. The GFCI should be rated for the same ampacity as the circuit it is protecting. For example, a 15 amp circuit should be protected by a 15 amp GFCI. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. This will ensure that the GFCI is installed correctly and will provide the intended level of protection. It is also important to test the GFCI after it is installed to ensure that it is working properly. The test button on the GFCI should be pressed to simulate a ground fault. If the GFCI does not trip, it should be replaced. In addition to GFCIs, there are other types of ground fault protection devices that can be used to protect against electrical shock hazards. Firstly, there are ground fault circuit interrupters, which are similar to GFCIs but are designed to protect entire circuits rather than individual receptacles. Secondly, there are equipment ground fault protection devices, which are designed to protect equipment from damage due to ground faults. These devices are typically used in industrial settings. When selecting a ground fault protection device, it is important to choose the right type for the application. GFCIs are suitable for protecting individual receptacles in residential and commercial settings, while ground fault circuit interrupters are suitable for protecting entire circuits in industrial settings. Equipment ground fault protection devices are used to protect equipment from damage due to ground faults in industrial settings. In addition to ground fault protection devices, there are other safety measures that can be taken to reduce the risk of electrical shock hazards. Firstly, it is important to use properly insulated electrical cords. Damaged or frayed electrical cords can expose live wires and create a shock hazard. Secondly, it is important to avoid the use of extension cords whenever possible. Extension cords can overload circuits and create a fire hazard. If an extension cord must be used, it should be rated for the same ampacity as the circuit it is connected to. Thirdly, it is important to keep electrical equipment away from water sources. Water can conduct electricity and create a shock hazard. Electrical equipment should never be used near sinks, bathtubs, or showers. Fourthly, it is important to educate children about electrical safety. Children should be taught not to touch electrical outlets or cords with wet hands. They should also be taught not to insert objects into electrical outlets. By following these safety measures, it is possible to significantly reduce the risk of electrical shock hazards and to protect people from injury or death. The NEC is a complex and comprehensive document, and it is important to stay up to date on the latest changes and revisions. This can be done by attending continuing education courses, reading industry publications, and consulting with electrical experts. By staying informed about the NEC, electrical inspectors and contractors can ensure that they are providing the highest level of electrical safety. And to add some more information about grounding to help protect against electrical shock. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to flow back to the source, causing the overcurrent protection device, such as a circuit breaker or fuse, to trip and energize the circuit. This helps to prevent electrical shock hazards and equipment damage. There are two main types of grounding. Firstly, system grounding, which connects the neutral point of the electrical system to earth. This helps to stabilize the voltage and provide a reference point for the system. Secondly, equipment grounding, which connects the non-current carrying metal parts of electrical equipment to earth. This includes the metal enclosures of appliances, motors, and other electrical devices. The purpose of equipment grounding is to provide a path for fault current to flow back to the source in the event of a ground fault. When a ground fault occurs, the fault current flows through the equipment grounding conductor back to the source. This causes the overcurrent protection device to trip and energize the circuit, preventing electrical shock hazards. The equipment grounding conductor must be sized according to the NEC. The size of the equipment grounding conductor depends on the size of the overcurrent protection device protecting the circuit. The equipment grounding conductor must be large enough to safely carry the fault current back to the source. In addition to grounding, bonding is another important safety measure in electrical systems. Bonding is the connection of all non-current carrying metal parts of an electrical system together to form a continuous electrical path. This includes metal conduits, metal enclosures, and metal water pipes. The purpose of bonding is to equalize the voltage between all metal parts of the electrical system. This helps to prevent electrical shock hazards in the event of a ground fault. When a ground fault occurs, the fault current flows through the bonding conductors, equalizing the voltage between all metal parts of the electrical system. This prevents a person from coming into contact with a metal part that is at a different voltage than the surrounding environment. Bonding conductors must be sized according to the NEC. The size of the bonding conductors depends on the size of the overcurrent protection device protecting the circuit. The bonding conductors must be large enough to safely carry the fault current. Grounding and bonding are essential safety measures in electrical systems. They help to prevent electrical shock hazards and equipment damage. It is important to ensure that all electrical systems are properly grounded and bonded according to the NEC.